We are the RoboJackets, the student organization for robotics at Georgia Tech. This is our 5th year competing at the IARRC, and this summer we are competing with our new and improved robot, Sedanii. Sedanii was originally constructed in May 2018 to compete in the 2018 IARRC. We based its chassis off the Losi Baja Ray 1/6 scale RC truck. Starting from the stock chassis, we removed all of the unnecessary components and replaced them with our own bent sheet metal, milled aluminum, and 3D printed components to mount our hardware. An Intel Nuke controls our robot's high-level perception and motion planning. Low-level steering and speed control is handled through a microcontroller and circuit board inside our robot's control module. Between the last competition and now, we upgraded our main control board, added multiple cameras for a wide-angle view of the track, and implemented accurate speed control. The final major addition is an improved e-stop system. It relies on streaming packets with a timeout system, so that if the remote is too far from the robot to send a command, the robot is automatically e-stopped. The new remote also has significantly greater range than previous remotes. As in past years, our software stack is built on Robot Operating System. This makes it easier to develop modular software for our robot. Last year we ran Sedanii using a neural network trained from a human driver. This approach proved hard to debug, so we developed a layered traditional software stack. The first layer is perception, which uses image data to find white boundary lines, orange cones, and direction signs. To find boundary lines, we use an adaptive thresholding operation to find parts of the image that definitely contain lines. Separately, a Laplacian edge detector creates a noisy edge image. By sampling points we are sure are lines in the Laplacian edge image, we can flood fill and extend them to have a noise-free image of the full boundary lines. Cones are found using a mixture of canny edge detector and color matching. Individual cones can be determined with the use of the watershed algorithm. From there, we can determine the relative size of the cones and compute the distance with trigonometry and the pinhole projection model. For sign detection, a canny edge detector finds general shapes. We can then match these shapes to a known arrow shape with the who moment shape descriptor. Found arrows are then classified as left, right, or straight. We use a variety of traditional computer vision techniques, including color matching, edge detection, shape matching with hue moments, and adaptive thresholding. The second layer is mapping, which synthesizes the perception features from all 3 cameras and our IMU into a cohesive view of Sedanii's surroundings. We represent our map as a collection of obstacle points in the car's local coordinate frame and keep a local history map of the past few seconds. The third and final layer is trajectory planning, which finds a feasible path through the map. We parameterize our path plan as a sequence of arcs and give each path a cost based on the angle of turning, obstacles hit, and other factors. We use simulated annealing to optimize our path in real time with respect to a cost function. Our team has worked hard over the past year to prepare our robot for competition. We look forward to seeing you all at the 2019 IARRC.